Ambassador Rangachari, Deputy Director General Brigadier Dahiya, most respected Mrs. Subramaniam, distinguished invitees, distinguished fellows of the Institute, the friends from the media. I'm extremely happy and proud that on this special occasion I have been invited to address this erudite audience in this great institute. 50th year of the institute is something very creditable, and this is one occasion where we pay our tributes to the founder and the people who brought up this institute to this level of national and international acclaim. A think tank for the country in an area where you can sit close to the agency and be away psychologically and look at it, criticize it, and provide valuable inputs. It's a very unique arrangement that we have in India. ISRO too is 50-year-old, theoretically 52-year-old, started again by visionary scientist Dr. Baba, Dr. Sarabhai, who had a clear outlook on what India should do in the area of space. And when in the modern space era, several countries who took up this activity were looking at that as a medium for showing their one-upmanship. Here there was a program which was started looking at the people, the common man in the country. A society-centric, people-centric program which gave relevance for undertaking such a program in the country. I salute those visionaries. Dr. Sarabhai's vision, Professor Satish Dhawan, who built up the necessary organizational structure within and the interfaces with the user organizations in the country to execute that vision, and all their successors who shared that vision. And that is the vision for the future of Indian space endeavor. To be relevant to the society, to the people, to be part of the development process of the country, to become part of the value chain of those institutions and the people of this country, and to do that in a self-reliant manner, and also to bring in more and more brighter minds into this endeavor. This is what we are looking at. I have put one slide there that shows the vastness of space and what we can do in this area. Space is considered the last frontier of humankind. And when we talk about space or outer space, it starts essentially from an altitude of nearly 100 kilometers above the surface of Earth. It goes through the solar system, it goes to the entire universe and probably the multiverse that the scientific community of the world are trying to understand over centuries. So when the space exploration provides that excitement and engagement that enriches the knowledge of humankind about his or her existence, the life on Earth, how the universe evolves and how it is going to be in the future. That is one part of this study. So when we talk about the mission to Moon, a mission to Mars, mission to understand the phenomena that is occurring in the solar system and specifically the Sun, it is that part of the activity. When we do a space exploration, when we go near, when you go do that in situ, it can be done using rovers, robotics. can be also with human in the loop. And there we talk about a human space flight, manned space flight. Then also, space provides a wonderful place, a benign environment for manufacturing, whether it is drugs or metals or things of that kind. People also talk about a habitat being created in our neighboring planet Mars, maybe a few decades from now. And as part of that process, Cape Moon as an intermediate station where from lot of activities could then start. So this is the first part of the space endeavor, the space exploration. It is exciting. Then comes the technology to enable this activity to be done and also to facilitate the applications that we are talking about for the human welfare. We need technology. The first part of it is how to reach the space transportation. What kind of assets we need in space, and how do we ensure that those assets are safe there, like the assets that we have on Earth today. If we depend on the satellites for our day-to-day activity, how do we ensure the safety of that, the security of that, technically and otherwise? And finally comes in what way we can help the humankind through the communication satellites, through the Earth observation satellites, and the navigation satellites. And how do we build systems to ensure all these happen? In fact, this is the engagement of all space-faring nations in the world. Priority changes, the vision changes. That is something unique to each country. And India has its own vision, its own priority in this area. Often the question is asked, where do we stand with respect to others in this area? And if you look at these space-faring nations, we can count nearly 15 of them, those who are actively engaged in creating space assets, that is satellites, and maybe half a dozen who have the ability to launch the satellites into the orbit. About 50 countries who are actively engaged in use of these systems with the necessary ground infrastructure as well as institutions for using them. Where do we stand in this global arena? There are two studies which I can quote. One is done by an organization called Futron of USA. The other one is by Japanese Institute of Science and Technology. The Futron has been conducting this study since 2007. Comparison of these 15 organizations on 50 metrics, qualitative and quantitative. And India has been in the 5th, 7th or 6th position since 2007. The first one being US, second one Russia, third one the European Space Agency, a consortium of more than 20 countries of Europe, then Japan, China, India, followed by Canada, Brazil and other countries. For the last 5 years, we have been 6th in this area. This report is available on the website. And they also indicate the relative improvements that each country is making over its counterpart in specific areas of space activity. At some point of time, they said India is a global leader in remote sensing. Later they said India is developing capacities, that is through an institute, to execute its future vision. Recently they said India is developing the launch capability to put its own satellites into orbit. So this kind of statements are made by them. But I should say mostly qualitative. The Japan Institute of Science and Technology brought out a study very recently looking at the specific elements of technology application and science, and looking at the quality, versatility, reliability of its satellites and launch vehicles across all portfolios of space activity, and gave them points. Again, India is there in the 6th place in overall. That is one point. I would take a few minutes to tell in each one of these plots that I have depicted here, where does India stand? If you look at the first block, that is the planetary exploration and the study of solar system, I was asked to talk about Moon and Mars, what we are doing in that area. Chandrayaan-1 is very well known. We did orbit a spacecraft around Moon in the year 2008. We also provided that as a platform for international cooperation, inviting foreign scientists to put their instruments on that. Technologically, India for the first time went out of the gravity of Earth to another object, that is Moon, traveling almost 400,000 kilometers, 4 lakh kilometers, and precisely orbited a spacecraft around Moon. And we were there for more than 300 days, and we conducted experiments. And we set up the necessary facilities. We had the spacecraft, we had the launch vehicle, all done in the So this was a major technological milestone at that point of time. We also provided that platform for the international scientific community, and from that instrument, a major discovery was made about the availability of water molecules in the environment of Moon. So that was another major milestone of that period. When we did this Mars orbiter mission recently, which is mostly documented and well known, 51 missions that were taken up till then, and now it's 53, had very low success rate, especially in the early periods. US, Russia, Europe, they did it successfully. Japan did not succeed. China tried to piggyback with Russia, and they had a mission in the year 2011, but that mission did not go beyond the orbit of Earth. It's a Phobos grand mission. So it was in this context the effort of India should be seen, that is on one side. In 2010, we started this feasibility study, and from concept to fruition, India took 4 years. With the launch vehicle available with us, that is the PSLV XL, whose capacity is almost 1/10 that of the rocket that America used for putting the MAVEN into the orbit. MAVEN is a contemporary mission to Mars. But what we used is our ingenuity of moving to a location using the propulsion of the satellite, and also designing a unique mission in which the minimum energy transfer from Earth orbit to Mars orbit was made possible. It was a complex mission, but we executed that. For the first time, we had a very long PSLV flight of 47 minutes trying to get that particular injection condition required for it. This was one major deviation from the conventional path that we took. The second part of it is, for the first time, we were dealing with distances in millions of kilometers, from 400,000 to 4 lakh that we dealt with in Chandrayaan. We moved into a travel of 660 million kilometers along a heliocentric path, that is an orbit around Sun. A spacecraft that has to be navigated very precisely to finally reach on that particular day, September 24th morning near Mars, at a distance of 500 kilometers plus or minus 50 kilometers. After going through the influence of Sun and all the planets. This was another challenge. And to direct the spacecraft in that direction, 300 days well in advance, precisely, was the challenge, and that we could do. This was the second milestone that India achieved. On that day, the global community, which are skeptical about this whole mission, changed their stance. And then they said, okay, let us see what happens from now onwards. We also had to deal with the communication with such distances. And here for the first time, we faced the communication delay. And on September 24, 2014, when we did that operation, the signal was taking more than 12 minutes to reach the spacecraft. But to understand what is happening in the spacecraft, we had to wait for 12 minutes, long 12 minutes. All of you would have experienced it on that day. But our job was to build systems in the spacecraft as well as on the ground for this communication, and also to locate the spacecraft very precisely at such distances with very high level of accuracy, which we did. And for that, we needed also other global stations, and we used the NASA's ground station for that purpose. And it was a great teamwork of experts from different disciplines. And the success finally is dependent on the level of detail that one can get into, looking at all areas where it can fail, from our own experience, from the experience of the earlier missions that US or Russia had done, and trying to find out solutions and preparedness for the contingencies. All these helped us finally to achieve that successful September 24th morning event. So this is something what India did. And there what happened? India became the first country in the world to achieve that in the first attempt. We don't speak as a country, it is a group of countries. We became the fourth agency in the world to have an orbiter around Mars. And the objective was primarily technological, that is to be there, and we achieved that successfully. Now the instruments are doing their job, trying to find out. 6 months of life, that is guaranteed. It could be much more than that. That is to be seen. When it comes to the human in loop and robotics, this is one area India has not entered in a very major way as compared to the other countries that I was talking about. India is making its beginning by looking at the critical technologies in this area. And we are going to have in the next month, December 2014, a test flight of our GSLV Mark III, in which the crew module that is required for the human space flight is going to be tested for its re-entry characteristic step. That is an unmanned crew module, but we would see as it enters the atmosphere at 100 kilometer altitude, what happens to the thermal fluxes, how it experiences that, and how it withstands that. This is something which is happening. Looking at the next column, that is space transportation, we have our PSL, which has launched not only the Indian satellites, but 40 foreign satellites. And a reliable vehicle, a versatile vehicle that has done several types of missions and sought after by the international community. And recently, in the year 2014, we had the launch of Spot 7 remote sensing satellite using PSL. Spot 6 was also launched earlier by the same PSLV. Several major satellites for 19 countries were launched by PSL. GSLV. In January 2014, we proved not only its functions precisely, but its Indian cryogenic engineering stage. This was a landmark in Indian space technology, something which we started in the year 1992 as an indigenous development when we were denied the technology for this cryogenics engine. The determination of the country, of ISRO, to do it alone finally worked. It's a very complex thing. There are only 5 or 6 countries who have this technology, and we achieved that. And our future launch vehicles are going to have this cryogenic technology. So that has been a very major achievement that we have. Capacity-wise, GSLV can launch 2.2 tons into geostationary transfer orbit. And what we are now embarking on is to have that capacity doubled, to get into 4 ton to 4.5 ton using GSLV Mark III vehicle, for which we have the experimental flight planned in December 2040. And where do we stand in the international arena in this area? China has a launch vehicle which has operational launch vehicle with a capability of 5.5 tons in GT. Europe has Ariane 5, which goes up to 11 ton into a geostationary transfer orbit, and US has nearly 13 ton. Russia has 10 plus ton. There are developments going on. China is talking about a launch vehicle that can go up to 8 or 9 ton into GTO. That's a capability that exists today. So we are moving into a direction for GSLV Mark III, which should be ready for its developmental flight in another 2 years' time. On the drawing board, we are looking at a launch vehicle that should be able to put a 6 ton to 12 ton class satellite into the orbit. That is our future direction, that is on paper at the moment. On space assets, I should say India has got a wonderful constellation of satellites. 10 communication satellites as of now, state-of-the-art communication satellites. And we are enhancing our capabilities. We are also trying to catch up with the state-of-art technology even for the future years. So this is something happening. High throughput, K-band communication satellites that could handle data rates of 100 gigabit per second. That is our target for the next 5 years. Enhancing the capacity certainly is part of the agenda, and that is taking place at the moment. Coming to Earth observation, we have today one of the best constellations of the world. And in the year 1995, India's IRS-1C was the best civilian satellite. And we continue with that edge over the other satellite operators. And our satellite data is used by several foreign countries. And they have data acquisition systems where they receive it also on commercial basis. Today, if you look at, we have the microwave imaging capability. We can look at our land and water resources. We can have high resolution remote sensing data. There are 4 satellites of that class which can go even up to 1 meter spatial resolution. And we are moving into 0.6 meter in the coming year with the Cartosat 2C and 2D. We are moving into 0.25 meter imaging capability with Cartosat 3. It should happen in about 3 to 4 years' time. That's on one side. On microwave imaging, we have today ability to look through our kharif crops or look at the flooded area in the presence of cloud, and that imaging is in C-band. We are getting into X-band, where we should be able to look at the objects, and we are working today with NASA for a satellite to be launched, to be built together with synthetic aperture radar in S-band and L-band, which is going to be used not only looking at the forest biogas, etc., but also for disaster management applications. In the area of weather, we have been having an INSAT system since the 80s. But if you look at the last year, we had an INSAT 3D satellite. It's a very versatile satellite with a better imaging capability and also ability to get the profiles of temperature and humidity up to 40 kilometer altitude. And if you look at the Violent cyclone, if you look at the recent Hudhud cyclone, INSAT 3D played a very major role in providing information to the India Meteorology Department 48 hours in advance on the cyclogenesis and the movement of the cyclone system. So there the benefit is that save lives through the early warning system. But we need to have again hot standby there. We are going to have INSAT 3D also, and more and more such systems are going to come into play. Ocean plays a very important role, and we have the OceanSat series. And OceanSat 2 scatterometer was the only scatterometer available in the world till March 2014, which was used by NASA, NOAA, as well as EUMETSAT for their operational forecasts. And that scatterometer was decommissioned in March, and we are now building another one to be launched soon in that area. So in all these areas, in remote sensing or Earth observation, India has its own prime position globally. And what we are looking at is to keep that edge. And all these remote sensing satellites, except the INSAT series, were looking at the Earth from a polar orbit. That means once in a day, or maximum twice in a day, they can take an image. And we are now building a platform from the 36,000 kilometers, which can continuously looking at this region and take pictures as and when required at 50-meter spatial resolution. And this is again going to provide capability for disaster management and also for certain strategic applications. Navigation is another area where India has entered into a very major way. We have the GPS system, we have the Galileo system being built, we have the Luna system which is in place, and China has its own navigation system which is getting built up. Japan also is building their own navigation system. India decided to have its own system, Indian Regional Navigation Satellite System, with a constellation of 7 satellites that provides you assured availability of the navigation signal with 20 meters or 10 meters positional accuracy. So this is in addition to what we would get from the other global navigation systems. We also have a mechanism here to improve the positional accuracy of the GPS signals, which is already operational, certified for civil aviation applications already. So this is something that is happening in that area. Again, conjunctive use of communication or the navigation or the Earth observation systems brings a new dimension to the possibilities of application. And there we have also the institutional interfaces with the central government departments and the space agencies. Currently there is a very major move going on enlarging the scope of the space application into the other government departments too, and almost 65 government departments are now planning to use space in their regular activity for their planning process, to aid in policy making, to monitor the various programs, improve the governance, etc. So this is something that is taking place in the country today. When we talk about the technological capability, how do you benchmark that? Apart from saying that we have a reliable PSLV or reliable GSLV. Soon after the launch, we talk about an accuracy of the orbit in which the satellite was injected. And we have a band which is specified. But when we talk about a geostationary transfer orbit to which GSLV D5 put the GSAT for communication satellite, it is a small pillbox of about 20-30 kilometers over a distance of 20,000 kilometers that we are able to achieve. And here the launch vehicle is navigating itself, measuring its position and steering the vehicle to that final destination. And that accuracy is finally determined by the accuracy of the sensors that we make here. And that is a strategy. When we talk about a capability to image the Earth and see objects of 0.25 meter or 0.6 meter or 1 meter, that shows two things, that you're able to point that satellite very precisely to that location where you want to take image. And we are also able to get signals from such small objects. Our capability in the area of optical systems and control systems, that is what it shows. When we talk about the communication satellites, they are used for several applications. Government uses strategic, community uses that. Then we have the commercial users who are all there actually. But for the first time, when we made GSAT-7 satellite in August 2013, that had its footprint over the entire Indian Ocean region. And this community understands what does that mean. In 4 frequency bands, ultra-high frequency, S-band, K-band, C-band. So this is something which is important. So space provides a platform that can be used by the strategic users, government users, commercial users, and also for the societal application. It's a question of how do we make use of it, when we make use of it, and how do you ensure its availability when you require it. And here we come to the last portion, to the security of these space assets. We talk these days about the space debris. When there are so many satellites, nearly 1,000 communication satellites in the orbit, and maybe less than 100 other types of satellites in various orbits. What happens to them once their life is over? What happens to those elements which get disintegrated during the life of the satellite? What happens to the final stages of any rocket after it does its job of putting a satellite that goes around? These are all objects which go with very high velocity, and we call them space debris. And how do they affect the operational space assets satellites? Are we able to catalog them? Are we able to predict their movement? Are we able to see whether our active satellites are safe from them? Or how do we move them around and ensure their safety? So this is a new area of study. And today the word coined for that is space situational awareness. And many experts in this room know the vastness of that subject in the civilian domain as well as the military domain today. Debris are created intentionally. They are also generated unintentionally due to technical problems that take place in various satellites. So there are groups in the international arena looking at avoiding the intentional creation of space debris through guidelines and gentlemanly arrangements. And there are groups or experts looking at all these debris, and there are supposed to be nearly 15 to 16,000 as of now going in these orbits. And there are forecasts given on the proximity of such objects near our satellites. And we do have our ability to understand some of these aspects too. So when we depend on space assets becoming part and parcel of our life in any domain, then it is essential that we ensure the security of them physically, electronically. This is other part of this subject, that is the space security. And at the moment I have covered most of what I wanted to say, and maybe 10 minutes we could spend on a couple of questions And I assure you what I can answer, I will answer. Some of them I may not be able to answer. Some of them I cannot answer.